Okay, so in the torque coupling and speed coupling, they both have advantages and disadvantages. So just by the name of torque coupling and speed coupling, you probably already realize in torque coupling, we add torque of the two input device. In speed coupling, we add speed of the two input devices. Therefore, in a vehicle, at low vehicle speed operations, what we want is a lot of torque to drive the vehicle for either accelerations or to overcome the static friction. Therefore, at low vehicle speed operation, ideally we would want to add the torque to use torque coupling. At high speed vehicle operations, we would want to add speed, but because at that time maintaining power to maintain the vehicle operation is more important than torque demand. In general, at high vehicle speed, torque is the most aspect that you're looking for. So therefore, to design a system using just torque coupling or just speed coupling may not be the best system to satisfy all kinds of driving demand. Therefore, we have another mechanism which will include both torque coupling and speed coupling, where torque coupling can be used for low-speed vehicle operation and the speed coupling can be used for high-speed vehicle operations. If we look at this chart showing here, we would have both torque and speed coupling. Well, we have one electrical motor and one engine. In this diagram, if you look carefully, the engine is still connected to the sun gear. The motor is connected, but has two clutches, two gears with a clutch in between. The first gear actually is connected to the shaft of the engine output, the transmission output, if you look. And that gear has a clutch number 3. So in other words, if clutch 3 is engaged, your motor drive shaft is connected to the engine output shaft. If clutch 2 is engaged, your motor is connected to, if you look at it, it's connected to the ring gear of the planetary gear system. So therefore, in this design, it depends on which clutch is engaged. If clutch 2 is engaged, the system is in a speed coupling mechanism. If clutch number 3 is engaged, then the system is in a torque coupling. So if you look at torque coupling, for example, clutch 2 is disconnected and clutch 3 is engaged. So motor is driving the output shaft of the engine, and then altogether they will drive the sun gear, and the sun gear torque is transmitted to carrier and to drive the vehicle. In this case, the ring gear needs to do something, because the ring gear, if you let the ring gear free, the planetary gear system will not rotate, it will not transfer torque. So therefore, we need clutch number 2. If you look at diagram here again, the clutch number 2 is going to lock ring gear. So when clutch 2 locks ring gear, lock 2 lock ring gear, clutch 2 open, and clutch 3 engage. This is a torque coupling system. But if clutch 2 is engaged, clutch 3 is open, and lock 2 is open, this is a speed coupling system. Next, we want to get into, as I mentioned, the planetary gear systems. Now, previously you look at already 2 planetary gear-based systems. One is for the speed coupling, and one is for both speed and torque coupling. In this section, we're going to look at more detail about how the planetary gear system would work and how it can carry torque from input to the output, or how it can summarize the 2 input devices and put the power to the output shaft. The diagram here shows the powertrain layout of the Toyota Prius hybrid. In this diagram, on the top, it's a side view of the powertrain. What you look at it is, on the right is a 4-cylinder engine that is connected to the carrier. So the engine is connected to carrier in this system. It's different from the previous 2 examples that we just looked at. The generator is connected to the sun gear, and the ring gear is connected to the output. So if you look at the lower right corner, that's cross-section of the planetary gear system. You can see the outside, the yellow gear is the ring gear. The very inside is the sun gear, the purple one. And the green is the four planetary planetary gears sitting on a planetary carrier. So that one is the carrier that is connected to the engine. In the previous example, if you remember, the carrier is connected to the output. But in that case, you have two input. One is the motor, one is the engine. So the two input to ring gear and sun gear, the carrier would summarize the speed. But in this case, it's a power split device or torque split device in the future, as we refer to. Therefore, the configuration is different. So let's move to the next slide, which will show you a better explanation of how the system will work. On this diagram is designed for the Mariner hybrid planetary gear system. Now, before I show the planetary gear system, I want to start with the vehicle electrical drive part. So if you see on the diagram, this is a front wheel driven system, and there shows a battery and an electrical motor. The electrical motor is driving gear N1, and the N1 driving gear N2M, and that yellow gear coupled together with N4, and the N4 driving N5, and then the output of N5 is driving the front wheel, the front axle. So in this set of display, this vehicle can be operated in electrical mode. Now, in the Mariner hybrid, the electrical motor is rated at 75 kilowatts. Therefore, this system can be driven electrically for a certain speed at a certain acceleration rate. If we add additional hybrid components, and you will see here is the engine coupled to a planetary gear system. The engine also is connected to the carrier, just like the Prius did. The sun gear is connected to a generator. At this point, the ring gear is not connected to anything yet, but that is where we want to discuss this before we get into the ring gear. So if you look at it, if suppose the ring gear can take some torque, that will be the case later on. We'll discuss it. So the engine driving the carrier, and the carrier is driving the sun gear. And the sun gear is coupled to the generator. So the generator would generate electricity when the engine is in motion. And that electricity is delivered between battery and the motor. So therefore, they're sharing the common DC bus. That energy from electric motor can be used to charge the battery, or it can be used to drive the motor, and the motor would drive the final drive. Okay. So that's one energy path flow. So if you look at how energy flows from engine to generator to motor, that energy flow is in a series direction. So therefore, sometimes this is referred to as a series operation. On the other hand, we know that on a planetary gear system, all the three gears, all the three outputs needs to be connected to something. Otherwise, if one is freewheel, the system are not able to transfer torque. So in this case, the ring gear has to be connected to something. Otherwise, the way that we just explained will not work. So therefore, we need to introduce another set of things that will connect the ring gear to actually the output to the final drive through a set of gears. So if you look carefully, the ring gear now is connected to N2, and N2 is driving N2E. That N2E is mechanically linked to N2M and N4, so they're on the same shaft. Therefore, engine torque now can be transmitted through sun gear to ring gear, and then from ring gear to the final drive. So if you look at this energy flow, the engine power is delivered from engine to ring gear, from ring gear to the final drive. And then motor can also deliver power to the final drive at the same time. So in this operating pattern, they are in parallel. And the previous one that I discussed is in series. So therefore, this system can be considered as a series and a parallel operation. It combines both systems in one place. Apparently, you have two electrical machines, one for the generator and one for the electrical motor. So this diagram basically show you how it operates. How exactly the planetary gear system are going to operate? Well, this diagram will show you a little bit detail on the equation that I wrote earlier. If we look back at the diagram, again, this is the planetary gear system. The outside, the ring gear. The inside is the sun gear. In the middle, between sun gear and ring gear, is the planetary carrier. If we specify the number of teeth on each of them, the ring gear teeth nr, the sun gear teeth is ns, then the carrier speed is equal to sun gear speed times a ratio plus ring gear speed times a ratio. That ratio for ring gear, that ratio is nr divided by nr plus ns. Well, the nr is ring gear number of teeth, ns is the sun gear number of teeth. So basically, you can see that the sun gear coefficient is ns divided by ns plus nr. The ring gear portion is nr divided by nr plus ns. So that's how you summarize the speed. So whenever the carrier is moving, its speed is equal to the summation of ring gear and sun gear, each with a coefficient. Let's move on to the next slide. Oops. Okay. So look, something happened. Cannot move the slides. Okay, sorry. So we'll look at the carrier speed is equal to, again, sun gear speed plus ring gear speed, each with its gear ratios. Now, if we multiply torque of the carrier on both sides of the equation, just like illustrated over here, we know that the power in the system will be balanced when we neglect the losses in each of the gears. Now, we'll discuss the losses in a later time. So Tc times omega c, which is the carrier power, will be equal to Tr times omega r, which is ring gear power, plus Ts times omega s, it's the sun gear power. Or Pc is equal to Pr plus Ps. And then we can plug in the equation that we have from last slide. You can see that, well, the Pr is equal to Nr over Nr plus Ns times omega r times Tc. So that's the ring gear power. And then sun gear power has a very similar expression. So sun gear power plus ring gear power is equal to carrier power when we neglect the losses. Because this expression, power is equal to omega times t in a mechanical system. T is torque, omega is speed. Therefore, we right away can identify that the carrier power and the sun gear power, which they also related to their torque. So therefore, you can find out the ring gear torque is proportional to carrier torque, and the ring gear torque is proportional to carrier torque, and sun gear torque is also proportional to carrier torque. So therefore, this is why this system is sometimes called a torque split, because on each of the output gear, in this case, the input gear is the carrier. The output gear is the ring gear and the sun gear. Each of the output gear has a certain percentage of the input torque. And the speed of the ring gear and the sun gear, the summation is also equal to the input speed of the carrier. So the operating of this system is that if we look at the system, because the vehicle speed is related to ring gear speed. Now, in the previous diagram, we already shown that ring gear of the planetary gear system is connected to, the ring gear is connected to the final drive. So ring gear speed is proportional to vehicle speed. So at any given time, the ring gear speed would be given. Okay? If the number of teeth and the number of teeth of ring gear and sun gear, they are both given as well, you will be able to calculate the ratio between ring gear speed, sun gear speed, and carrier speed. So this example, we have an engine. Okay? The engine operates at 100 kilowatts, When it is operated at 2000 RPM, it will give you the best efficiency. And this happens to any engine. There is a power and a speed where you will achieve the best fuel economy, the best efficiency, the lowest emissions. In the system design, we have 32 teeth on the ring gear and 30 teeth on the sun gear. And the vehicle is operating at 45 miles per hour. Since we know that the ring gear is connected to the final drive, therefore we can easily calculate the ring gear speed based on the vehicle speed, knowing the diameter of the wheel and the gear ratio. In this example, we calculated that the ring gear speed is 2632 RPM. And we know that the carrier is the engine where we want the engine to operate at 2000 RPM. So the only left unknown is the sun gear speed. Using the speed coupling expression, we can, on the right hand, you can see that the carrier speed is equal to these two added together. We know the number of teeth, we know omega r right now. So the only unknown is omega s, because omega c is what we expected. So based on the expected 2000 RPM, we can calculate the omega s is 482 RPM. So in other words, in this system, if the vehicle operating at 40 miles per hour, and if we control the generator so that the generator is operating at 482 RPM, we can easily achieve the engine speed at 2000 RPM as we expected. And in this case, the engine will provide 100 kilowatts power at its best fuel efficiency. Now, of course, controlling the speed of a generator is not that easy, not like controlling the motor. So you may have a little difficulty to maintain that at exactly 482 RPM. So you may find yourself at 450 or even 550 RPM, but that's okay. What it means that if the generator speed is not exact 482, the engine speed will not be exact at 2000. But with a few percentage variation, you can still maintain the engine at its best fuel efficiency. So that's the idea. If your vehicle speed change, you can control the generator speed so that you can maintain the engine operating condition at 2000 RPM or around 2000 RPM so that it will give you the best fuel efficiency. This is just an example. It's not saying that 2000 is the best efficiency. It depends on the engine type of engine, the speed range of the engine, and the rating of the engine. So it has to be dealt on a one-on-one cases. So in this operating example, that we know the engine is operating at 2000 RPM, 100 kilowatts, so we can calculate how much torque is generated by the engine. It's 477 Newton meters as we calculate on the chart. And given this torque on the carrier, we know the ring gear torque is proportional to the carrier torque. So we can calculate the ring gear torque to be 337 Newtons meters. And then the sun gear torque, which is generator torque, is also proportional to the carrier torque, and then we calculate it to be 140 Newton meters. The ring gear torque is transmitted to the final drive, directly to drive the vehicle, but the sun gear torque is transmitted to the generator, which is going to generate electricity. Now, we already calculated from last slide, it is going to run at 482 RPM. So we multiply the speed of the generator 482, 140 Newton meters of torque on the generator shaft. We can easily calculate the generator power is 7.1 kilowatts. So the ring gear torque is 92.9. That is transmitted directly to the final drive, from engine to final drive. But 72 is going to be transmitted to the generator to become electricity. That 7.1 kilowatts electricity can be used to drive the motor, or it can be put in the battery. It depends on how much power from the vehicle, the power demand from the vehicle. Now, this example, if the vehicle is in acceleration operating condition, and it needs 120 kilowatts. It needs 120 kilowatts on the wheel. Now we know that almost 93 kilowatts is already coming to the wheel from the engine, from the ring gear. So that's 93 kilowatts. And then the generator generates 7 kilowatts. That 7 kilowatts can go to the motor as well. Now you add this 7 and that 93, you also got 100. So you're still 20 kilowatts short to drive the vehicle. Where do you get that 20 kilowatts? Apparently, we don't want to overrun the engine. So the engine is still going to operate at 100 kilowatts. The only way we get is from the motor. So the motor can provide additional 20 kilowatts. Now, the motor is going to need electrical power because the generator is only providing 7. You now want 27. So that 20 kilowatts needs to come from the battery. So in other words, engine power plus battery power is equal to the vehicle power. Assuming there's no losses in the system. Of course, in a real system, you have to consider the losses of each component, the transmission, the motors, the batteries, and so on. But in this case, for simplicity, we neglect the losses in each system. We basically calculate how much power is needed to drive the vehicle. That's 120. And then we find out that the engine will provide 100 kilowatts, and the motor is going to provide, the motor actually is 27, but 7 also from the engine, but 20 from the battery. So that's how it works in the system. So in a planetary gear-based hybrid like this one, the control strategy is designed such that the generator speed is always controlled or manipulated so that the engine will run at a better fuel economy. So on the chart here, it has the display of the procedures that how to control the system. Basically, every time the vehicle controller continuously monitors the vehicle speed. Based on that speed, it can calculate the ring gear speed. Based on the ring gear speed and the desired engine speed, it will calculate how much speed is needed for the sun gear. And then it will control the generator output so that the generator speed is maintained at this desired speed. Therefore, your engine speed is also at a desired speed, which will give you a better fuel economy. So in this case, the control input, you can see it's mostly just the vehicle speed and the power demand. So the vehicle speed will determine how to operate the generator speed. And the power demand is going to determine how much power the engine needs to generate and how much power needs to be supplied by the battery. Or in some other cases, how much power needs to be used to charge the battery. So the battery can be operated in both conditions, charge or discharge, depends on the vehicle demand. If vehicle demand is high, if vehicle power demand is high, you can discharge the battery. If vehicle power demand is low, and then you can charge the battery. So you can determine what kind of vehicle operating condition and then determine how to run the engine and how to run the battery. In the real world, of course, the control is very complicated. In a hybrid system, this diagram shows the Prius controller diagram. You can see that the hybrid vehicle controller is also called a hybrid vehicle ECU, electronic control unit. That is interacting with a lot of components in the vehicle system. It takes a lot of input and try to manipulate those inputs and produce control output. You can see that the component interacted with HVECU include the generator, the motor, the boost converter. Now we are going to discuss what the boost converter is all about later on. And additional like AC compressors, the air conditioning systems, the power steering, the braking, the regenerative braking systems, and the hydraulic braking system. The input to the HV controller would be the component information, how the component is operating, the battery conditions, for example, the SOC of the battery, and the speed of the motors, generators, engines, and so on. So a lot of this information are processed by the ECU and then controlling all the components so that you can achieve better fuel economy. And the better fuel economy is achieved by optimizing the power of each component. And then within each component, the operating condition is also optimized. In this control, I want to give you an example. So what happened to the Prius evolution? The Prius vehicle, when it first came to the market in 2000, the fuel economy is around 35 to 39. But a few years later, it was increased to 45, and then again 53, again 65 mpg. Over the years, if you look at the basic architecture of the Prius hybrid, it did not change very much. Even though the motor size has changed some designs, speed ranges, and so on, but the power ratings of the battery, the engine, the motor, it did not out of the order, which means they're still within a small range of allowable design changes. But the fuel economy improvement was not, it was incremental. I mean, it changes so much. So why did that happen? So apparently a lot of these benefits were derived from optimizing the vehicle control. So because the hybrid vehicle control is very important because it involves a coordination between the different components and a vehicle operating condition. In a conventional vehicle, you only have one component, the engine, you have to control. Therefore, the control is much easier. You basically control the engine to satisfy the driving power demand and speed. But in a hybrid, you can always manipulate the operating condition for each component, the motor, the battery, and the engine, so that you can optimize the operation of each component. As a result, you can get a better fuel economy for the vehicle system. So this one probably shows a better layout of the Prius vehicle system. This, if you look at the chart, this is the Toyota Prius 2005 version. And in this diagram below the vehicle, I'm showing the system arrangement. If you look at the arrangement, the front wheel, this is a front wheel drive system. The front wheel is connected to a reduction gear. And between reduction gear and the planetary gear set, there's an electrical motor, 50 kilowatts. The planetary gear is connected to the engine and the generator. So this is the same as we discussed the planetary gear showing on the previous slides. The engine is connected to the carrier, and the ring gear is connected to the final drive. The motor is actually only sitting on the same shaft of the ring gear output. So it's not driven by the ring gear anyway. So what it means that the motor can freewheel. It can be freewheel, and the engine will still be able to drive the vehicle without using the motor. So the motor is assisting the driving. So the motor and the ring gear are actually in a parallel style. Okay, and the generator is connected to the sun gear, which is a 28 kilowatts generator that is connected to an inverter. And the motor is also driven by an inverter. And the two inverters are both connected to the battery and the battery DC-DC converter. What we have here does not show the DC-DC converter between inverter and the battery. But in the real system, there is an inverter to link the inverters and the battery. So the DC-DC converter is transferring the 200 volts battery voltage to 500 volts DC bus voltage. Okay. So this system consists of engine, 57 kilowatts, an electrical motor, 50 kilowatts, and a generator at 28 kilowatts. The battery is a nickel metal hydride battery rated at 200 volts, 6.5 ampere hours, which is about 1.3 kilowatt hour. So this is a very typical hybrid vehicle. For larger vehicle like the Chrysler Aspen and GM Yukon and some other vehicles, SUVs, you're going to need about 2.2 kilowatt hour battery in place of this battery pack. In a plug-in hybrid, apparently this number needs to go much higher. Not typical energy rating for a Prius type plug-in hybrid is about 7 kilowatt. You can drive 20 miles. For SUV type hybrid, you're going to need about 10 to 11 kilowatts. Again, you can drive 20, maybe 25 miles electrical range. So that's the Prius hybrid. The Highlander hybrid is also from Toyota. This configuration is very similar to the Prius hybrid. In fact, the Toyota system has been designed in almost every hybrid that it develops, including the Lexus brand. In this design, the front wheel is exactly the same as the Prius hybrid. However, it did have a 50 kilowatts motor at the bottom. If you look at the bottom, that is connected to the rear wheel. The rear wheel is connected to a 50 kilowatts motor through a reduction gear. So this vehicle is a truly electrical four-wheel drive. the rear wheel is driven by a 50 kilowatts motor. The front axle it itself is a hybrid. Again, it's similar to the Prius with a planetary gear, engine connected to the carrier, motor connected to between ring gear and the final drive, and ring gear is connected also to the final drive. The generator is connected to the planetary gear through inverter to a battery, and this battery is also 6.5 ampere hour, but it is 288 volts. So simply, they have more battery cells connected in series to form 288 volts. Each of the nickel metal hydride battery cell is 1.2 volts. They put 6 cells to form a module, which is 7.2 volts each module. So in the Prius, they have 34 modules in series. In this one, they're going to have a lot of, in the Prius, they have 28 in series. In this one, they have 34 in series. Okay? You can see that one of the difference that you can observe on this one is that they have a much bigger electrical motor, 123 kilowatts, much bigger generator, 82 kilowatts. The battery also bigger, 45 kilowatts. And the rear wheel also have a 50 kilowatts motor. In other words, the electrical power of this system is much bigger than the Prius. Of course, it's partly due to the fact that this is SUV, much heavier, much bigger. But on the other hand, Toyota claim that this is a muscle hybrid, which means they're focusing on the drivability, the performance of vehicle, other than the fuel economy, even though you do get better fuel economy of this vehicle. In particular, the rear wheel drive, the rear wheel four-wheel drive with the motor placed on the rear wheel is making a lot of sense, because that rear wheel motor, 50 kilowatts motor, will probably cost less than the traditional four-wheel driving system. So therefore, putting this motor would save some additional cost to make a four-wheel drive. On the other hand, the electrical motor mounted on the rear wheel is 50 kilowatts. At low speed, low vehicle speed, even at a stall, the motor can provide a lot of torque to drive the vehicle, which gives you much better drivability in four-wheel drive conditions at extremely hazardous road conditions. The operating of this planetary gear system, we already had discussion about it, but now let's go to a little bit more detail in 6 different operating modes. The first mode is at the startup. In the Prius hybrid, in many other hybrids like the Highlander itself, or even the Ford Escape and American hybrid, the Ford Fusion hybrid, the Nissan Altima hybrid. In all of this hybrid system, they use a planetary gear-based, very similar torque split system. So at the starting, if you look at the chart, the engine is off. Only the electrical motor is powering the wheels. And this can run up to 34 miles in the Prius, and 30 miles in the Nissan Altima, about 35 miles in the Escape and Mariner hybrid. What it means that if your acceleration is pretty gentle and your vehicle speed is below 35 miles per hour, 34 in the Prius, the engine is off. Now, of course, that also depends on how much energy is available in the battery, depending on the Prius prior driving cycle condition. So normally, the battery would have enough energy to reach this speed. So in this case, we call it starting and a low speed motor-only operation. That's motor-only. The next slide shows in a certain acceleration, or in a vehicle driving, anytime that you try to accelerate with a more than moderate acceleration rate. In this case, the engine would be kicked in, so the engine is turned on. When the engine turns on, the engine will develop a lot of power, and that power is split by the power split device. Most of the power will go to the final drive through ring gear, and small portion of the power will go to the generator. And the generator electricity is supplied also to the motor. So the motor taking power from both generator and a battery, so you can see the arrows pointed. So the motor taking both power from battery and generator to drive the vehicle, and the engine power also goes to ring gear to drive the vehicle. So you have a lot of power, a lot of torque available to drive the vehicle in a certain acceleration condition. So this is also called a combined mode. A third operating mode is at normal driving, at highway driving or highway cruising, and then even at moderate speed cruising like a 40, 45, 50, 55 miles cruising speed. In this case, the engine is maintained on, and the engine will produce sufficient power to drive the vehicle. That power, though, from the engine is split between ring gear and generator, or ring gear and sun gear. The ring gear power goes directly to the final drive. The sun gear power goes to the generator, which generates electricity, and that electricity is delivered to the motor and battery. Normally, in this case, the battery is idle, so the electrical motor is using that power to drive the vehicle. Now, the battery can be charged at times. It depends on the SOC of the battery. If the battery SOC is pretty high, so it will be sitting idle. So in this case, again, most of energy will go to the final drive through ring gear, but some of the power will go through generator and motor to the final drive. And this can be seen from a previous example where we had 100 kilowatts power from the engine, only 7 kilowatts go to the generator motor, but 93 goes directly from ring gear to the final drive. So this is still true for most of the highway operations. About maybe less than 10% goes through generator and motor, but 90% go directly from engine to ring gear to final drive. The portion of energy that goes from engine to generator to motor would have very low efficiency because the energy is converted a few times. But the energy goes directly from engine to the final drive. There's no conversion directly from mechanical to mechanical. Therefore, the efficiency is pretty high. Since only a small portion goes from engine to generator to motor to the final drive, so that portion, even though the efficiency is low, but it does not constitute a big portion of the total system power. But on the other hand, we discussed that because we control the generator speed, we can manipulate the engine speed. So therefore, the engine will operate at a much better fuel economy point, a much better efficiency. So in that case, what it means that even though we have a small portion of power that is not very efficient, but because the increase of engine efficiency is so much that it's going to overcome that efficiency the efficiency that you lose from that parts, and you actually gain more. For example, if you lose 5% on the engine generator parts, okay? Now, you are going to gain not 5% more, but you probably gain a lot more on the engine operating side because you can easily shift engine operating efficiency from 25 to 30%. And that's very easy. And that 5% gain is on a total engine power. But that 5% that you lose is only a small portion of the engine power. So therefore, the overall system efficiency is still higher on highway cruising for this type of hybrid. The reason? Because we are doing better in manipulating the engine operating efficiency. Now, in conventional vehicles, this is done by controlling the CVT, but the CVT itself is pretty low efficiency too, maybe 85%, 90% efficient. And plus, no matter what CVT you have, you still cannot operate the engine at its best fuel economy operating condition. So therefore, the system in normal operation, in highway cruising, is still more efficient. Another operating mode is the regenerative braking. In regenerative braking, you can see that the wheel is driving the motor. So the motor is now becoming a generator. Well, it takes the power from the wheel and it generates electricity to charge the battery. At the meantime, it's creating the braking torque to slow down the vehicle. So this is the regenerative braking mode. The last operating mode is what we call the stationary charge. In stationary charge, the vehicle is stationary, but the engine is turned on to charge the battery. This normally does not happen very often, except where the battery energy is pretty low. If the SOC of the battery in the vehicle system is pretty low at the startup, so the system will start the engine to charge the battery so that your system can be maintained in normal operating condition. One thing you should be aware that in many of the hybrid vehicle systems, there's no alternator. There's no small generator that can charge the 12 volts battery or the 14 volts battery in the vehicle system. However, you still need that 14 volts battery for many of the auxiliary equipment use, such as your wipers, your door locks, your seat, powered seat, your headlights, tail lights, okay? And all of them are going to need power. That power is coming from the 14 volts battery. And that 14 volts battery needs to be charged. So usually there is a DC-DC converter that links the high voltage battery and the 14 volts battery. It takes power from the high voltage battery to charge the 14 volts battery. So the 14 volts battery will maintain the normal operating condition of the system. If the high voltage battery SOC is too low, so the system should start the engine to charge the battery, because otherwise your system may not be function normally. Some of you, if you have driven Toyota Prius, you may also have noticed that if you forget, for example, to lock your door, and if your door is open, not locked, but if your door is not closed properly, in fact, the system does not go into a sleep mode, which means some of the ECUs and some of the system are still going to consume power. So after maybe a few hours, the 14 volts battery is drained. But since the key is not plugged into the vehicle, the 14 volts battery is not charged from anywhere. Therefore, the battery may die at that point. So therefore, it's important that the vehicle is doors are closed properly, that all the system electronic control unit will go to sleep mode. Therefore, you can save power from setting everything to sleep. Therefore, you can conserve energy on the 14 volts battery. So that's one of the things that we have to be careful. In a hybrid system, there is an engine and there's a motor, there's a power electronics. Therefore, the overall system architecture is much more complicated. Not only that, the cooling system will also become more complicated because the different components in the system will need different cooling mechanisms. For example, engines can be cooled at much higher temperatures, probably more than 100 degrees C. But the power electronics and motors are usually at a lower temperature, especially the power electronics. The current silicon-based power electronics normally will only operate up to, say, 125 degrees C in their silicon chips on silicon pin junctions. So those operating temperatures need to be maintained by a cooling system. So if your cooling liquid temperature is too high, you may exceed the operating temperature of the silicon chips. Therefore, you may be burning the system. So therefore, we need a cooling system just for the power electronics and electrical motors. On the other hand, you still need your traditional cooling system for the engine itself. Okay? So the diagram here shows the cooling system designed for the Toyota Prius. On the diagram in the middle, you see the engine, the power split device, the generator, the planetary gears, and the motors, the reduction gears. So you can see that the motors and the power electronics are cooled from a loop, and the engine is cooled from a loop. So if you look at the lower left corner, look at the engine. Connected to the engine is a cooling pipe with a 3-position valve, and that is connected to a heat storage tank, and then that is connected to an engine coolant system pump, and then the radiator. And after the radiator, it goes to the engine. So therefore, this loop from engine to the tank, and then to the pump system, to the radiator, and then goes back to the engine. So the engine heat is dissipated in the radiator. But just above the engine coolant radiator, there's another radiator, even though they are mounted at the same place, but it is a separate radiator. And if you follow the arrow pointer directions, coming out of the radiator, the liquid will go through pipe to the inverter on the top right corner. It says the inverter. So liquid goes to this power electronics to cool the power electronics first. So the cold liquid goes to the power electronics and cooled down pretty good temperature, and then it moves to system overflow reservoir, And then after that, you can see the hydraulic drive coolant system pump. So there is a pump to pump the air, pump the coolant out, and it injects the coolant into the electrical motor and the gear cooling system part. And after that, it comes out at bottom left of the motor system, and it goes to the radiator. So this system is cooled usually at a lower temperature. A typical coolant temperature is about 70 to 80 degrees C in the power electronic motor cooling loop. But it's usually around 100, maybe 110 degrees C, or even 120 degrees C on the engine side. It depends, of course, the season of the operating condition. That gives you a rough idea on how those electrical motors are cooled, how those power electronics are cooled, and how it is designed in a Prius, a system similar to a Prius hybrid. The Honda Civic, on the other hand, is a very different concept than the Prius hybrid. In this Honda Civic design, if we look at the diagram below the vehicle, you can see that it is also a front-wheel driving system. It does have a 5-speed manual transmission or a CVT. Before the CVT, or between the CVT and the engine, there's an electrical motor. In the older design, it is a 10 kilowatts motor. In the newer design of a Civic, it is a 15 kilowatts motor. And the motor is powered by an inverter, and an inverter takes power from also nickel metal hydride battery, but it is at 144 volts. So this is also called a common shaft design, and it is a torque coupling. It is a parallel hybrid. Even though position-wise, it looks like a series from engine to motor to vehicle, but energy flow wise, it is a parallel hybrid. And you can see that in this system design, even though the newer model has 15 kilowatts motor, but that 15 kilowatts motor is usually rather small to drive the vehicle alone. So if you happen to have the chance to drive a Civic hybrid, you will see that the engine will start very frequently, even at very low vehicle speed. So therefore, I would say that this type of vehicle, because the motor size is limited, therefore it cannot be used as a plug-in hybrid, because you will not be able to take advantage of onboard electrical energy. If you do, even if you do have a large battery pack, you may be able to take advantage of the larger battery pack. For example, you can put more regenerative braking energy in the battery. However, it is also limited by the size of the motor, because the motor is the one that can generate power during regenerative braking. 15 kilowatts motor means you can generate maybe at 16 kilowatts during braking. So you are really not taking 100% advantage of regenerative braking. So therefore,